started. So last time, and this is a brand new lecture, it is called Lecture 13. And last time I made a suggestion out there for selected topics for people who wanted to know more about stuff. And I had like 3 responses total, and they were both getting at object-oriented. They wanted a review of the object-oriented features. I think you actually wanted it too, yeah. A review of object orientation, inheritance, interfaces, and all those different concepts. So this lecture is Lecture 13. It's added on. It's on bhecker.com website, so you can go ahead and take and download it and stuff. I'm going to see as far as I can get through it. It's about 60 to 70 slides long. But I'm going to go through it because it's a review of the entire course, focusing on object orientation in terms of how it's implemented in Java. So it's a nice review. If I don't finish it, don't worry about it. You can finish it on your own. It's nothing new. There's no new material being presented. It's just a high-level overview of everything we've done so far. So we'll look at superclasses, subclasses, protected, and I'll try to go through the easy stuff really quickly, just to freshen up. And it's nice to review lecture actually for the final exam as well. And I don't have a clock with me, so someone tell me when it's like 6:30 or 6:45. That way I can stop. So, will you tell me? Or the TA can tell me. TA, can you tell me when it's 6:30? Tell me when it's 6:40. How's that? Okay. Unless I get tired by then or finish by then. Who knows? So, okay. And we all know that the final exam is on Monday at 5 o'clock. Okay, good. You can take both exams. If you're in both classes, you can take them both at the same time if you want, actually. If you're in the Android class and you're in the Java class. It's kind of tough to take them back to back, but you don't have to wait till like 6:30 or 7 to take it. Object orientation, inheritance is the form of software reusability. So this is what I'm talking about. So object orientation has a PI, abstraction, polymorphism, inheritance, encapsulation, as I covered before in the class. And just to reiterate the point, we use inheritance for reusability. And it gives us reusability of objects. So new classes are created from existing classes. We absorb the attributes, the behaviors, and we add in our own information. We override methods. We redefine inherited methods. So we have overriding and overloading as main concepts. We subclass that inherits from superclasses. We have direct superclasses. So we can have superclasses explicitly inherits through extends. And we have indirect subclasses that inherit from 2 or more levels of the class hierarchy indirectly, because if you think about it, when you extend one class from another, you get everything above it. So you can actually directly inherit by using this class extends this class, and then you indirectly get everything, is what that's referring to, everything above it in the hierarchy. Polymorphism, as an example, was also covered in this course, and that's the P in the PI. This is the I in PI. So polymorphism is write programs in general fashion and handle in a variety of different classes. So by this basic definition, it is nothing more than being able to use things in a generic kind of fashion, whether you're using a class as a polymorphic class, an object as a polymorphic, which basically is giving you a wide variety of different options to apply towards one concept in a generic fashion. Not having to worry about types, if you want to think of it that way. So we have the ability of one object to morph into something else or to do something else. Abstraction is seeing the big picture. It's the underlining abstract concept of these objects that are existing in this object-oriented world. The introduction and introducing the concept of protected, we didn't actually talk about that. So I sort of like, and this slide actually comes from a review lecture from a really good textbook by Prentice Hall. It's kind of out of print right now. It's actually kind of old. But it's it's from the year 2000, so it's like 12 years old. But it was a nice kind of, and I just had this hanging around, and I used to use it in an old Java programming course. It's a nice kind of recap, actually. And I'm looking at this going, yeah, I didn't talk about protected methods or protected members access. And I did talk about it in the C++ class, however, and it means the same thing. And we don't actually have to work with this very much because, you know, we don't necessarily deal with it. But anything protected means that through inheritance, it's public, but from main, it's not. So it's the same thing as it meaning in terms of private data members, but we don't actually use protected as a mainstream kind of concept. In fact, you don't really do that in C++ for the most part, only because what you're looking at is building a strong hierarchy where things are private inside of the class and they're public from a method perspective. So you're keeping all your data private, you're keeping all your members private. So it's very rare that anything would actually have to become public outside of its own environment. Through inheritance, if it's private, it's inherited. So it's automatically protected and it's automatically inherited from a public perspective. So not to confuse you completely on the access methods, but in terms of the access methods, just think, you have basically everything you have in C++, you have in Java in terms of the capabilities, and everything inside of the class should always be private. Everything outside of the class, you want accessible outside of the class, is public. Through inheritance, you get protection, and protection comes out through inheritance. We have relationships that we talked about in the course. We have an is-a inheritance. So an is-a, the object of a class, is an object of a superclass, if you remember that part. We have a has-a, which is a composition type of relationship. So the object has an object of another class or as a member of that particular class. So as an example, going back to person and student, student has a method that is part of person. So if there's a method that says get name, set name, that's inside of person, student also has that. So that's where the has-a comes from. I usually just refer to it as is-a option because a student is a person, so it doesn't have everything that a person has, which by default it really does. So we also looked at class libraries in this particular class, new classes which are inherited from other classes, and building hierarchies of classes. In fact, the collections class was a good example of that, where everything in the collections class builds upon a hierarchy. And so when we make a linked list, it's a list, and it's a collection, and it's a this, and it's a that, and it goes all the way back to object. So in terms of someday software that might be constructed from standardized, reusable components like hardware, which is pretty much the goal in terms of the inheritance and the class libraries. So creating more powerful software is essentially the goal with that. Can we keep the volume down in the back? It's like ultra loud here today. I feel like I'm yelling over the back room here. Excuse me. Don't talk. Yeah, thank you. Otherwise, I'm going to take that attendance list away, because that's obvious right there. All right. All right, so in terms of inheritance, as an example, we have a rectangle that might be quadrilateral, I can't say that word, quadratical, whatever. Can't talk today. We have different superclasses and subclasses that can be involved in terms of the shape, if you think back at the shape example. And what we look at the bottom is the free-form tree-like structures created a hierarchy from shape. So shape would be the lower level. We could create a triangle, we could create create a cone, we could create a square, a rectangle, all sorts of different things in terms, and this is what we mean by inheritance, that they all root down to the same concept and that they have some concept in common. So you want to keep the inheritance, and here's a better example actually. These are lines that you can't see, but there's arrows here up at the top. So we use the keyword extends, if you remember that. We covered this. So we have class two-dimensional shape extends shape, and then we have private data members of the superclass that are not directly accessible to the subclass, so we have setters and getters that set the shape members so that we can access them from the subclass. All other variables are kept keep their member access rights as well. So actually everything keeps their access rights, if you think about it. So in the superclass, so we have, and this is just a review and going into the protected, which is I really didn't cover very much in this particular course because it's, it's kind of one of those things that, a lot of teachers actually don't like it when people make things protected because it's either private or public, right? So, but we'll see why in this example here. And in your assignments, you never really had to use it for anything. So public members are accessible anywhere the program has a reference to a superclass or a subclass type, which is public. Private members are accessible only in the methods of that particular superclass. Protected members are intermediate protection between private and public. So it depends on where you're accessing it from, whether it's public or private. Only accessible by members of superclasses, subclasses, or classes of the same package. So it has to be part of the family. If it's not part of the inheritance family, it's not going to be accessible. It's going to be private. And if it is part of the family, it's going to be public, which is where that protected comes into play. So we have subclass methods that can be referred to as public or protected members of by name. Overridden methods accessible with super, dot, and a method name. So you can actually override the methods as well as overloading them, as we discussed in the course. So we know that objects of the subclass can be created as objects of the superclass, but the reverse aren't true. This is the casting. So we can take a person and turn them into, a student and turn them into a person, but we can't take a person and turn them into a student because there's no student information inside of that person. So if you remember, and I call this upcasting, so there's a slight difference between the terminology of the slide set, because the slide set's actually sort of dated, but not really dated. Nothing is really dated when it comes to Java because everything's still relevant, but slightly different terminology. I still refer to things as data members and member functions. The Deedle and Deedle book actually calls things fields. Yeah, I don't know. I like member functions. This lecture set calls them variables and data, which is kind of interesting as well. But anyway, long story short, remembering the upcast concept, which I call the upcast, it's basically objects of subclasses, which would, in terms of what the concept is. So suppose you have many classes that are inherited from one superclass. You can make an array of superclass references and treat all the objects like the superclass object. If you haven't done the assignments yet, you'll discover that this is what you're doing with the last assignment. This is exactly what you're doing. You're taking all of the students and the teachers and you're making them into people or something of that nature. You're upcasting them back up into their superclass object, and so you can put them in an array, and so you can populate each other's objects, the arrays inside of each of the objects to make the students aware of the teachers and the teachers aware of the students, essentially. And that's one of the main reasons why this particular feature actually exists, because you want to be able to treat the objects as like to kind and store them all into an array or some sort of structure. It doesn't have to be an array. You can store them in anything or do anything you want with them. You don't have to store them. You can just use them for comparison reasons, seeing if this object is another object. You may also upcast to use it for, let's say, a parameter to a method call or something as well. We have an explicit cast by convention, converting a superclass reference to a subclass reference. They call it downcasting. I call it upcasting. Just letting you know there's many different ways of describing the same concept. What I call the up, they're calling it down because I see it the opposite way around. I turn the hierarchy upside down when I view it. But long story short, we're talking about what I've been calling for the entire course, upcasting. It's referred to as downcasting here because you're downcasting it. You're making it from a broader thing down to a narrower. So you're narrowing down the concept into the person from the employee or from the teacher or from the student. So you're breaking it down into a smaller component, which is why it's referred to sometimes as downcasting. Some people just don't like to deal with all of the different variations and they just call it casting, because then you don't have up, down, or sideways or anything else to worry about. So know that it's an explicit cast that's being performed. It can only be done when the superclass reference actually refers to the subclass object, superclass object. We also have the instance of operator, which is an important one to remember. You'll need that one if, actually you could use instance of in the last assignment as well. You can say if P is an instance of circle, then do something. Return true or return false if P is equal to circle or is a circle. So instance of refers to the is a relationship. So overriding methods. So we know we can override and we can overload. We can override methods. The subclass can redefine superclass methods. When you do that, you're overriding. When you redefine the method with the same signature. You're overloading when you change the footprint or the signature. depending upon how you want to call that, how do you want to label that. So when the method mentioned in the subclass version is used, you can access the original superclass method by going super.method name. So it's overriding, but it's not overwriting. So overriding is essentially saying from this particular object's perspective, and this is where I go and I call it hidden. I say, well, the other one's hidden, and in this particular object we can access this method, and this is what the method's going to do. But if we go to super and we go super dot, we go back one level in the hierarchy, we have a totally different implementation of that method because we overrode it or overrid it. So we can call that as well. But if you don't specify anything, it's going to call the current objects method. So that's essentially the concept in terms of the overriding. So to invoke the superclass constructor, explicitly call the implicitly by the default. We've seen this before. We can call super. We can use super on here. Can pass arguments if needed as well. If you have a constructor in the superclass that takes on a certain number of arguments, you can pass them through the subclass up to the superclass. So by using super, essentially. So it's called explicitly, but must be the first statement. So remember, actually that's kind of an important concept. It must be the first statement in the constructor. If it's not, it won't be called because it can't do all of the other stuff. Because the original object that's being inherited from is created first. So if you create the implementation last, the object's already created. So you have to call that first to say, you know, super back, when that one is being made, after that's completed, then you're going to do your rest of your stuff, essentially. So, and we don't have to look about applets because we didn't talk about J-applets or applets in this class, so don't worry about the applet part here. We have an example here where we have a point definition, where we have data members, a constructor, and methods. This is a nice lecture to review the concepts if you have a you don't want to go through the directories and look at all the source code examples, but you want to see a kind of a clear line by line. And I'm not going to go through all of this stuff here, but it's basically showing you that this would be a good reference to use to review in preparation for the final. It's all the same code that we've seen before, but it has more commenting in it. So as an example here, it says the no argument constructor. I've been calling it the default constructor, although the slide doesn't say that. So that's what I mean. There's a little bit of difference, but it's no big deal. We have protected here in this particular case. It could be private. So unfortunately for you, there's no source code writing on the final, so you don't really have to worry about that. And there's no questions on access methods either, so you don't have to worry about that either. But here we have integer x and y, and we have a default constructor, and then we have an implicit call here to the constructor that occurs first. So we have the set point 0, 0 inside of points, so it's going to run a set point function. And then here's set point down here actually. So inside, this is actually kind of common to see. Some of the methods that are being invoked inside of the object can be called from the constructor, and you can reuse the same method. So remember before, when most of you probably did this, but who knows, when we created that first assignment, or even the dinosaurs actually, you can call set name, set number of legs and stuff from the constructor. Instead of putting the code in there, you're calling the methods, and so what ends up happening is you have reduced the number of methods you actually have to write, or just the lines of code that you have to write. Sort of like the way you reuse functions over and over in a program. Methods are done the same way. So here the constructor's calling this method, and the method's over here. And you notice we're not actually sending, we're not using a dot notation on here either. Just remember that, because you're inside of the object. So you're calling set point's down here. The constructor never returns a value, so there's no data type. It just says public pointer. So that's an important concept to remember as well. And if you're brand new, it's also important to know that you can have multiple different constructors, and the way you tell them apart is by the number of parameters that you're sending them. And the example continues, and we have, get this, get y, get x, and then we have down here, we have a public class circle that extends point. So if you don't have a textbook, this actually is a really good example to follow through. If you're still having problems with inheritance and you're still having problems trying to figure out, well, what do these classes look like and how you're supposed to create them? Because what you're looking at here is a really good kind of simplistic example of creating a class point and then doing all the sets and the gets and then creating a class circle that extends point that has a radius, and then on the radius we have a, we have a separate data member that we're adding to it along with x and y. And then we have different constructors, and we're using super in the constructors to go back and set A and B, which are going to be the 2 points essentially. And then we have another constructor. We're not using abstraction in this particular example, but there's another example coming up that will have an abstract method for the area, because we can create different types of areas depending upon the shape, and this is, that we're creating. So this particular one is good for the multiple constructors and for extending points. So if you remember, if you download the slide set, which is number 13 for those of you who came in late, and also for those of you who came in late, we're reviewing the entire course again because a lot of people had questions that they sent to me, and I was like, wait a minute, and it was just fundamental object-oriented stuff. So we're just taking more time to review everything. So anyway, if you notice on this right-hand side, you'll see what this example is actually supposed to be showing you. So you could search through the file if you wanted to actually kind of get at the constructor, the methods, the data members, the circle, the definition. And then we have an overriding in here. In fact, this is a good example of why you want to create that as an abstract class. To go back to the concept of abstraction, to talk about that a little bit earlier, we filled in a method body here for radius. And no, actually we didn't put it in points. So we don't actually have to have it in circle. We added set radius as a method in the circle class that we created. However, we could have created that as an abstract. If we did that, the whole entire class would be abstract. So we didn't put it in there. And we don't actually have to use it. It's not like a steadfast kind of rule where just because you're not going to use the implementation perhaps further down the road, you're going to essentially here, we're going to override the behavior on the get radius. Then what we're going to do is essentially, reinvent the wheel over and over again on each new class, which is nothing more than overriding. And if you override, well, then you actually have all of that implementation available to you. So you can, go back, treat the circle like a point, and of course, getting a radius on a point isn't really going to do anything for you. So here's calculating the area of a circle, getting the radius of a circle, converting it. So overriding the toString method. In this particular example, we're overriding toString. It's not overriding the radius because we didn't inherit another class. But if we did take this and inherit another class from it, we'd have to override it. Otherwise, the area of a circle is going to be different than if we take a point, turn it into a square or something like that, or circle. Well, I guess we could take a circle and use it in a cone or something in terms of putting the shapes together. But anyway, not to confuse you even further, but there's times in which it makes sense to actually create abstract classes. It's just when you do, if you think that someone would actually run that method of the of that class and get a wrong value, it makes more sense to make it abstract, because then you're requiring, if you inherit from that, if you use it, you're going to have to rewrite it to make it appropriate. So kind of eliminates some errors perhaps further down the road. There's no rule that says it has to be abstract though. So here's another example from inheritance. This is called inheritance test, demonstrating the is a relationship, and choosing swing. So the examples in this particular slide set are showing you all of the concepts that we've looked at all put together. So you've got, instead of like starting with baby steps, they're like full swing implemented and full everything. So this one's got the J option panel being used in it. And so, in fact, these are really good examples. Unfortunately, if you cut and paste, you're going to get the line numbers and the formatting and everything else. So it's probably better to go to the author's website, actually. And then the reference is at the end of the lecture. And download those examples if you're curious, actually, in terms of, or type it in instead of cutting and pasting. But here we have an inheritance test, and we have a main method in here, and the main method is essentially making some points, some circles, working with some string for the output. And then we're going to use the is-a relationship in this particular example. So we have point reference equals C, so we're assigning a circle to a point reference. This is one way instead of explicitly casting, using point inside of opening and closing brackets and casting a circle into a point and giving it a point. We're just saying it's going to be equal to. So as long as it's equal to, you're automatically assigning, in this particular case, the circle and making it into a point, because it is a point. You're referencing it as a point instead of a circle. Output's going to be equal to, this is the string essentially. And then using, here's the other word. I call this upcasting in the slides. Again, it's calling it downcasting, but hopefully at this point you understand the difference, or you know it's the same thing. So, so the casting of a superclass reference to a subclass data type to assign it to a reference. So you have two ways. By doing it this way, you are assigning it through an assignment expression, or you're doing it this way by casting it. So one's implicit, the other is explicit. You don't really have to know the terminology. You don't have to know what is which way. It's just nice to know that there's really two ways of doing it. You can explicitly cast it, or you can just implicitly kind of just assign it, kind of thing. Let's see, that's really all the examples showing you that's different in terms of the learning objective. If you go through the rest of the example, it's just showing you that it's taking the string that's created from all of the different outputs, and it's going to put it in a box, dialog box on the screen. So, and it looks like that actually, the output of the program. So, and that's nothing more than a window, a dialog window actually is showing you a message. So implicit subclass object to superclass object conversion. This is just a review of what I just went through on that particular example. The reference to the subclass objects may be implicitly converted to the superclass references. Makes sense, especially if it contains the same members corresponding to those classes, superclasses. When you don't need the subclass and you want to use it as a superclass, there's nothing wrong with casting it back. Referencing the subclass object with the superclass reference is that one way. In fact, the slide is just basically telling you there's two ways. One is to use the explicit cast, the other one is to use the reference, use the assignment. So here's way number one is right here, the assignment, and way number two is the cast, essentially. Believe it or not, you're actually not going to get anything that difficult on the final either. The concept of using an object that's subclass object as its superclass type is on the exam, and you should know that. The syntax for how to create the cast, not on the exam, that's what I'm saying. So, but you should know that you can take a subclass and use it as the superclass object. You can take everything and use it as object, which is the highest superclass object. It's important to know that, because then that is a relationship is like clear in terms of what it is you're doing. So let's see. Inheritance, we've seen that in terms of customizing existing software, creating new classes that add. So when we inherit, the goal of inheritance is actually to add. We want to take and we want to supplement what we already have and contribute something new to it and add to it. So if we're inheriting without adding, we should inherit. And if we're going to inherit and we're going to change the concept, we're adding so much, we're changing it, we're taking a boat and turning it into a car or something like that, or a chair and turning it into a car, that's wrong too. So it's just a supplement to reuse. So you might think of inheritance as a reusability kind of component. So reusability is key to large-scale projects because it saves work, yada yada. So we have more specifics in terms of the superclass. Usually they call it the narrowed down specific implementation, like point, X and Y. And then you get broader and broader, and you get more specific in terms of the concept as you go down into the hierarchy, because you have more information. It's just like, imagine if you had started with nothing and you built a bunch of knowledge the end result is an accumulation of everything else, everything before it, which is what you get in inheritance. So you get some pretty sophisticated subclasses further down the road. The subclasses are said to be customized. You start out with a car as an example, and you create a BMW, and then you create a Z3, and then you create 2-door and 4-door models of certain things, and you customize it as you come through. It's also actually called factoring it out to form the superclass. I don't use that terminology though, so don't worry about it. And as another thing as well, if you see something in this lecture, because it does come from a separate slide set, that terminology you don't understand, you can always send me a message. Otherwise, don't worry about it, because you're not responsible for any of this terminology either. You guys wanted to kind of from a different, I'm trying to give you this from a different perspective, essentially, and give you an entire overview of the entire course all in like an hour, so this is pretty fast too. So composition versus inheritance. So the is a relationship is inheritance. The has a relationship is the composition, having other objects as members. So I don't actually distinguish them two of them because they're both together. It's hard to have a is-a without a has-a, and vice versa. But technically, you could have a has-a composition. As an example, a person has a first name and has a second name, or has a birth date. They could have that whether or not you were using inheritance or not. But what is that? That's just, it's kind of stupid. I mean, why would we care about that? But it's members, data members of a class. But when we think about, is a student, is a person, that gives us a little bit more information. That's a little bit higher notched, I think. But anyway, the terminology is there is a relationship in terms of a composition, and then one of them that is explicitly, the is-a is explicitly referring to its inheritance. So, I don't know. So employee is a birth date. That's wrong. Employee has a birth date, yes. So if you think about just the way you say it, you're naturally going to say it, and you're going to get the association when you say it. Like, people have a birth date. That's a has-a. But is a person, is a birth date? No. So, but a person could be a mammal or something, is a mammal, or are we mammals? Yeah, I don't know. Anyway, long story short. Okay, so polymorphism. So this is one of the other topics that someone had mentioned that they, hey, I want some more information on polymorphism. So here's your grab bag of information for today. You write extensible programs with polymorphism because you're creating more functionality with each line of code that does more than just what you think it does, because you can morph it into anything you want. So generically processed superclass objects. Easy to add classes in the hierarchy because they're generic. Little or no modifications required in terms of the processing of it. And only parts of the program that need to have direct knowledge of the new class must be changed. So just think we're creating more generic. So polymorphism comes in multiple different forms. It's the ability of one object to change into another object. It's the ability to create a method that takes on multiple different types of objects by treating it. And when we say generic, this is another difference in the slide set versus my terminology. I never say the word generic. Instead, I say making it into an object or making it typeless, if you think about it. It's not really typeless, it's just universal. So the ability to transform, the ability to create methods that take on generic type of parameters, which are objects or people, lower subclassed objects. You don't have to, the definition of polymorphism doesn't mean that you have to take the parameter as an object, because you can actually use object as a data type, as a parameter type. But that's really low. I mean, there's no function. You're not getting anything with that, unless you're just going to print something out or do something, kind of basic. So usually you're going to take classes from a higher level. If you're going to create a dinosaur and you have Dino, and everybody's a Dino, then you're going to make it Dino. So that one method can take in all types of dinosaurs. And that's polymorphic, essentially. If you don't have to worry about switch statements, because we, it's just in here. I didn't edit this out, so. Dynamic method binding. That we did talk about. As an example, circle Triangles, shapes are all superclasses of shape. Each has its own overridden draw method. So when we override methods, we have one method in, we have a shape that has draw as in this particular example, and then we create a triangle and we have a draw in the triangle, and then we have a circle in the triangle, and we have a draw in a circle and a draw in a square. And what dynamic is referring to, and this is actually kind of the concept of the JVM and the Java environment, which is a little different than C++ actually, is that at runtime, when we use the object and the object's been created, we take whatever draw happens to be associated dynamically with that current object. We can actually take the object, turn them into other objects, and run all of the different draws on them if we wanted to. But we can automatically assume that whatever object we have, the appropriate overridden method is going to be applied, which is what that meaning. So it doesn't matter how many of them exist, we have dynamic method binding. And the binding, if you're not familiar with the concept, is essentially just taking and locating, finding, and referencing the correct method. And it's done at runtime, actually. And runtime is dynamic versus statically compiled stuff. So when you statically compile something at, before it actually runs, you're already telling it what method it's going to use and what data it's going to contain, and everything's kind of set. So you can call a draw using the superclass references, and then execution time, the program determines which class the reference is actually pointing to, and then uses the right draw. So it calls the appropriate draw method. So, which is one of the benefits of overriding, actually. We looked at final methods in classes, but we didn't program with this, and it's really not on the final exam either. But if you're interested in learning a little bit more about the concept, didn't cover it as well. We actually covered it within the first lecture of the course, believe it or not. It was a while ago. Declaring variables as final indicates that they cannot be modified after declaration. So they're like pi definitions. They're sort of like constant variables. They must also be initialized. Because if you think about the concept, you final, here's pi, and then later on you can't say, okay, pi is equal to, hey, you can't assign it to anything. So it has to be initialized along with the declaration. We didn't actually work with this though, but you should, leaving a Java class, you should know about that concept. It cannot be overridden, obviously, because it's final. So that's why, in some cases, especially in inheritance, if you think you're going to override it, you're not going to make it final. It's final. It's not. It's done. Static and private methods are implicitly final. Static means it's at a class level, if we remember that. Private means that it's not exposed, so it's already. If you inherit and you've got private data, it's already final because it's not visible in that inherited class. So the program can inline final methods. Did I talk about inline methods? The declaration, well, we don't have to worry about that. It's just a shortcut way of declaring methods. Actually inserting the method code at the method call location. So instead of creating the method ahead of time, don't worry about inline methods. You don't have to do that. In fact, not necessarily good practice either. Declaring classes, you can actually declare classes final. We didn't really do that in the programming examples, but you should know that that's also the case. Which means that you cannot be superclass, cannot be a superclass, so it cannot inherit from it if it's final, because it can't change. It's stuck. So why do you want to do that? Well, what if you've got something that it's basic functionality like a print or something, and you don't want it to be modified? Then you declare the class as final. All methods in the class are explicitly final if the class is final, obviously, because everything's final. Abstraction. So that was your 5-minute explanation of polymorphism. And also feel free to stop me as I go through this, because I'm trying to review the entire course and the object-oriented concepts. And in order to get everything done in one class period, I got to go pretty fast through this. Abstract classes and concrete classes. See, I don't use the word concrete classes either, but I did mention abstract classes. So concrete classes can instantiate objects and provides, basically provide specifics. It's inherently features that we've already worked with, however, without actually even calling them concrete. So abstract classes or abstract superclasses. Sole purpose is to be a superclass. We know that already because we can't make an instance of an abstract class. Hopefully you got that. Other classes can inherit from it, and they should inherit from it. That's why it's existing. And you can't instantiate objects. Can still define a constructor. The abstract class can still have a constructor. Too generic to define real objects from it, and you can declare the class with the keyword abstract, as we've seen so far. You want to know a little bit about abstract classes in terms of its purpose, because that's kind of, for the foundation of inheritance, the more abstract you are, the more you're delaying the implementation till later on in the hierarchy, which is a little bit more preferred, especially if the implementation is going to change. Concrete classes can instantiate objects. We actually saw that you can make you can refer to the instantiation of the abstract object when, if, let's say, for example, we take person and we make them abstract, and then we create an object from that student, and we create a teacher object. We inherit it from it, but person is abstract. We can reference person from the object of student and teacher from the inherited objects that are inheriting person. Because at the point that we've made the student or we made the teacher, we have instantiated a person. That's what, I don't call it concrete, but so don't let the terminology fool you, but you can actually reference that as a person, yes?
So, is there, then is that object class has the same sets of members?
It's defined from student or from teacher, whoever implemented it.
So if students have the age for the person as 21.
There's your problem. Yeah. If it wasn't, if you can make the instance, which is kind of useless because the data, if it was later implemented,
it will refer back to the same one, right?
It should refer back to the instantiated object that was created, like student or person, but you have to explicitly reference it. You have to say, person as a student, give me your age. Person as a teacher, give me your age. You can't get it from person. So there's not that much functionality. The only thing that you can possibly do with this is use them as like objects.
So it just exists for the subclass to use?
Yep. Yeah. So the instantiation is limited.
So the extents would be more of open to the superclass.
Superclass, yeah. We look at class hierarchies. Most of the general classes are usually abstract at the lower. So you get more abstract classes in the superclass category. Again, I have to kind of flip the hierarchy upside down in order for you guys to, because most textbooks flip it around. Anyway, whether you're a bottom-up or a top-down kind of thinker, the lower you are, the more narrow you get with the object concept, the more abstract you are. And as you're growing out, you're getting a little bit more specific, and your abstraction goes away because you're specific at that point. You're no longer abstract. Let's see. Adding new. This is just going through polymorphic examples. Rectangle. Okay, so I'm going to kind of skip through this because I already talked about this stuff. So new classes can be added easily. With polymorphism, one method can cause different actions to occur depending upon the object receiving the call in terms of it. Referencing, hopefully we know about references, can create references to abstract classes. That's what I just mentioned a few minutes ago. Can't instantiate objects of abstract classes, but you can reference the abstract class. And that would be, and just going back to the example I just gave you a few minutes ago, that would be like taking a teacher or a student and turning them into, referencing them as a person, and person as an abstract class. That's legal. Abstract methods make an abstract class. So any class that has at least one abstract method must be declared as abstract. And that's why it's abstract, because there's something in there that's not implemented. if you're going to create, there's a lot of people that think best practice, if you're going to create an abstract class, the whole thing should be abstract. It doesn't really matter. You can instantiate, you can have constructors in there, you can give data, because if you're going to if you're going to upcast to that abstract class, if you define it in the abstract class, you can get it. So going back to what you said, if person actually defines name and age, or was it age you were talking about? Yeah. And it's in there, but there's something else abstract about it, you can still get it from person. So it's accessible. Even though the class is abstract, you can still reference it through a reference of person for that particular object. Depends on where it is as to, or if it's not, you can take that person and turn him in fact, treat him as a student and go .name, or whatever, .age. Okay, so the keyword abstract is used. So any class with abstract methods must be abstract. Abstract methods must be overridden in the superclass. You can't not override them. Otherwise, the subclass must be abstract. So you can create an abstract class from an abstract class by not implementing them. So if you have the possibility of taking and creating an abstract class, then creating another abstract class from that abstract class, and then another abstract class from that. If you look at the collections package, you'll see abstract, abstract. Oh, look, implemented. It's just delaying the implementation. As long as you have one method that's abstract, the entire class is abstract. So you can inherit or extend, I should say, abstraction all the way through until the point, and a lot of people do it until the point where you actually want to implement it. And then when you implement it, all of a sudden, oh, nothing more is abstract, therefore you're no longer abstract. So nothing wrong with abstract classes. It doesn't mean that you can't put functionality in there. You can. And you use it, and it gets inherited. Abstract classes are inherited just like regular classes are. So the iterator class, if you remember, we actually talked about this in the collections package, but there's no collections questions on the exam, so I'm going to kind of skip through this. But walking through all of the objects in a container, the iterator is an abstract class example, actually, because it can take and iterate through anything, a list, an array, a collection of any sorts. So it uses a polymorphic programming kind of concept. You walk through all of the arrays of superclass references. You can draw methods on each one of the references. You can use the draw method as an example for iterator. So polymorphic behavior works with abstraction as well in terms of the concept, because if you make it abstract, then in terms of the implementation, it turns into, as an example, the area. So the area method, it's abstract in a circle, excuse me, in shape. That gets implemented in circle is going to be different than one that gets implemented in a different extension off of shape from a different, like a triangle or a rectangle or something. That's actually considered polymorphic behavior, because when you run draw or you run area or you run whatever that method happens to be by the same name, depending upon the type of shape it is, whatever implementation actually occurred last on it is the one that's going to run. So if it's, because in terms of the abstract concept, you're not overriding or overloading, you're implementing, which is the difference. So the reason why abstract methods are empty, they don't have method bodies in there. However, they can contain information, which is kind of tricky, but don't worry about that. I'm not going to ask you questions about any of this stuff, but I'm just letting you know that you can implement it and then make it abstract to a certain point by playing around with what it is you're doing to it. But for the most part, an abstract method does not have an implementation in it. It's not an implemented class. So in terms of polymorphic behavior, you've created the method. So the method exists. So the method that has an implementation eventually through an extended class, an inherited class, is going to have a different definition of that original method. So it kind of makes it polymorphic. Abstract classes morph into something, and their implementation completely changes. Well, actually, they get implemented. It's not really that they've changed, but the implementation is different, which is why they were abstract. You make things abstract because you can't really tell what you're supposed to do in terms of the implementation at this point. Because until the object is actually created, we don't know what it is. And as in going back, if we're going to draw something, do we draw a rectangle? Do we draw a triangle? How can we draw the shape if we don't know what the shape is? That's why you make it abstract. If you remember that part, you got it down. That's abstraction in terms of what you need to know for the final. You're delaying the implementation because you don't know. And if you pick something right now, it's going to be wrong. It's kind of like how people say, just decide, you can't decide, and then you make it abstract. You can't, because otherwise you're going to make the wrong decision eventually. So we have dynamic binding or late binding, which happens, we actually looked at this in terms of the classes as well, which is how we can get abstract classes. So it accommodates new classes, so object types don't have to be known at compile time because whatever we have to make in terms of the hierarchy is created at runtime. So it's dynamically created. And if a method is abstract in a lower class and we create an instance of an object that uses a different implementation of that method, that gets created dynamically at runtime as well. So we have the new updated implementation that's used in the subclass. I'm not going to go through this inheritance and polymorphic inheritance case example here, but there's another example here that you can look at that's going to go through this everything I just talked about a few minutes ago, showing you an example. And it's using the shape, and it's creating subclasses of point, circle, and cylinder. And I believe this is the one that's going to be doing this is the abstract class shape. Okay, I guess I will point it out. Abstract class shape. That's public, by the way. We can make classes public and private. There's no sense to make it private because it's just unless it's going to be final, because it's going to be not used very much. We have point that extends shape, and inside of point we have the set points, the gets, the sets and the gets, the two strings, the get name. Then we have circle in here as well. And what did we have abstract in point? We had area, and we had volume, and we had get name. So we just have return. We're returning a double from area and from volume, but we don't have any implementation in here. So we can immediately kind of tell that it's an abstract class. We definitely could implement some methods if we wanted to, but we're not going to in this particular case. So we have circle that extends point, inherits from point. We have, what do we have down on the bottom here? We have a get name that's implemented. If we leave one of these methods out, in fact, your Eclipse will tell you immediately. If you leave one of these methods out, area, volume, oops, I'm sorry. The only thing that's abstract here is string get name. These guys are not abstract. They're not implemented, but they're not abstract. This one's abstract. If we leave this guy out, we get an error message. If we leave the other ones out, we don't get an error message. So we have to implement the abstract method, which is what the rule is. Because you're basically saying it must be implemented. So in here we have get name that's implemented in both classes if you go through the example. So that's a long. And then we have the driver program in here as well that makes instances of these objects and puts them in an array of shapes. So we have circle, we are making some new point, a new circle, and a new cylinder. We have a shape array, and then we have an array of 3 shapes that we're going to create, and they're all going to be point circles, and we're actually putting 3 different types of shapes inside of the array. So we're upcasting it essentially to a shape. This is what you're doing for the last assignment, by the way. So this is not a bad example if you're still looking to see how in the world am I supposed to create that array if you haven't seen my video, which gives it away. But this example will essentially show you the concept in terms of taking objects and treating them like other objects, where there is a relationship for an array. It is. And then this one's looping through the array and printing out stuff in terms of what it is. Only problem with the casting and using objects in terms of their superclass identities is eventually you have to figure out what it is. So you have to come up with a check, which is what you guys probably figured out. Is this an instance of this? No. Okay, is it an instance of this? No, because it's almost like you took everybody and you took away their name tags, and then now you're trying to figure out who they are. So if you do that, you have to actually worry about the loop that you're going to have to go through, which isn't too bad. It's just an extra couple lines of code that you have to do after you've stripped the identity out of the objects to see what the objects are eventually. And that is what you'll have to do for that 5th assignment, actually, or the last assignment, I should say. And this is the output of that particular screen. It's just printing out the area, the point, volume, and stuff like that. Just kind of a simple example, actually. So let's see. Here's our creating and using interfaces, another example. So the interface is, hopefully you remember, it uses the keyword interface. So abstract classes have abstract before class. So the interface is an interface. We don't say interface class because it's not a class, it's an interface. And we implement interfaces, we extend classes. So it has a set of public abstract methods inside of it. Interfaces are very similar to abstract classes. Can contain public final static data using interfaces. So we have a class that specifies that it uses an interface with the keyword implements, as we've seen. Multiple interfaces can be used, separated by commas. How many classes can we extend from? How many classes can we extend from? 1. Remember that. How many interfaces can we implement? As many as we want. Which some say that's the reason why, because implements is kind of like putting a bunch of abstract classes in there and creating multiple line inheritance, if you think about the concept. Because if you create an interface, you're really creating an abstract class in some aspects, so you can only extend one class at a time. One object inherits from only one other object. You can only extend one object from one object. But you can implement as many interfaces as you want, so you can build in multiple line functionality. When you're going to do that, well, only when it makes sense. You don't want to implement interfaces that don't make any sense. If you're doing that, and as I mentioned before, sometimes they do that for tagging, because remember the is a relationship. You can automatically make everybody the same by implementing an interface, and then you get an instance of that interface that's in there. So they all have that commonality in there that you can use to create them all and put them all on the same level, which is nice. And you can also add in different functionality. So a class must define all of the abstract methods in the interface. So if you use an interface, you have to define all of the abstract methods. So you must use the same number of arguments as well in the same return type. So the interface is basically saying, here's a template, these are the classes these are the methods that we want you to implement in this class. So when you implement an interface, you're setting a contract that says we're going to have this in it. Because the other reason why you want to use an interface is to make some consistency. If I have a circle, a rectangle, solenoid, or whatever, I have all these shapes. I know I'm going to have a draw method because I'm going to create an interface. I'm probably going to implement, well, I could probably implement shape instead of making an abstract class. I could make it an interface, actually, same concept. And then in the interface, I'm going to have a draw method. I'm going to have a toString method or something. I'm going to have a print method or something. I don't know. And so I know 20 years from now when I come back and I look at this program and I make a new circle, I know I can go circle.draw because I know that method is there because it's part of the interface because this is a shape. So it's almost like saying because we're human and we have 2 legs and 2 arms, well, some of us are going to write with our right arms and some of them are going to write with our left hands, you know, but we both know, everyone knows how to write. So inside of our human object, we have a write method. So any human, we can ask, can you write that down? And they know how to do it, which is the same thing you get in programming because you want to make sure that, you know, who knows where this thing came from, but it's a human, so it knows how to write. It's a shape, so it knows how to draw itself. It knows how to print. Without interfaces, you have no consistency. Because you have no rules, well, unless you do it manually. You don't have to use an interface, or some people don't use interfaces at all. Don't use an interface, just use everything abstract. Well, you're stuck with only one class, extending from one class only, if you don't use interfaces. And then you're like taking a gamble. Did I implement the draw? I don't know. My compiler didn't tell me I didn't, so I guess I did. And then all of a sudden you have a circle that doesn't have a draw method in it, but it compiles and it runs just fine. But there's a method missing that you'd think would be there. Why do you do that? Well, because here's what ends up happening. If you're doing it yourself, you can control everything. If you're working with a repository of classes, you got 5 different programmers working on this project at the same time, You build implement the interfaces to make sure that you've implemented all the correct functionality. That Joe over here has got his object conforming and it has a draw method, and Mary's got a draw method, and everybody nobody has to communicate. You just implement the interface, and you've got everything you're supposed to have in there so that you're compatible and your object gets used by the main program, and the .draw method gets called on your object. It works. So you can have predict what kind of functionality might be used. You're not going to put something in an interface that's senseless, that's not predictable further down the road. But so for those people who asked about interfaces, gives you consistency, conformity, implies some rules, gives you tagging capabilities, and allows for multiple inheritance, and extends the concept of inheritance actually past the abstract concept, and works very similar to an abstract class. Using an interface is like signing a contract. That's a good bullet point. I will define all methods specified in the interface. Same is a relationship as inheritance. This is okay, so I call this tagging, because if you're going to use an interface in an object and everybody's using this interface, you can actually just have an interface that has a tag in it, like an ID. I came from ITU. And then oh, the object, where did it come? Hey, it came from ITU. It belongs to a particular class, or belongs to a particular interface, and you can tag it. And you can have other objects that say, hey, I came from somewhere else. It's kind of like the way transcripts are tagged. They usually have a letterhead on the top. The school you came from, it's tagged. The transcript itself probably looks the same as any other transcript. Well, hopefully it does. Different format maybe, but contains all the same information, hopefully. Using interfaces are used in place of abstract classes, or along with. This is deceiving. You can extend and you can implement all in the same class. You don't have to do one or the other. Used when no default implementation exists. So you want to create the default implementation. Typically public data types. Interface is defined in its own .java file. That's kind of deceiving because, in Java all the classes are in their own .java, all the interfaces are in their own .javas as well, but how do you tell a class from an interface? Interesting, everything goes into a .class file, .class. So interfaces and abstract classes and regular classes all look the same after they're compiled. They're all class files. So interface name the same as the file name, obviously same thing, same rules apply when you create a class. See previous interfaces, action listener. Actually, action listener, if you're in the Java class, you're implementing action listener. It's an interface class that gives you the onClick method. That if you don't include that onClick method, it's going to say, hey, where's your onClick method? You implemented this interface. This is what we get when we do swing, when we work with Android. We get the onClick method from the action listener. That's where that's coming from. It's an interface. Required to define action performed. This isn't a non-Android. It's onClick or actually we have an action performed in Android as well. So an example, previous hierarchy, replace the abstract class shape with an interface shape. You can actually do the same thing, and this is what this example is going to do here. And just notice the difference here. It's the same example actually, but instead of the word abstract here, instead of the word class, it says interface up here. So this is public interface shape. So know that you can use interfaces in replacement of abstract classes. They're just nothing more than abstract classes, really. And the example here is going to go through the entire program and give you that stuff. Don't worry about inner class definitions. We actually covered this last time, but if you wanted a little bit more information, it's in this PowerPoint as well. So till classes have been defined. At file scope, you can actually put a class inside of another class. There are no questions on inner classes. Subclass. It's not subclassed. It's just a class that's defined inside of another class. You can also define an interface inside of another interface. You can define an interface inside of a class. You can basically nest the whole thing if you want. More complicated, but you only do it when you're grouping items that belong together. So as mentioned before, that bank account that had action in there to deposit, withdrawal, and stuff like that, those objects that are performing functionality for the bank account can be defined inside of the bank account. When you compile it, believe it or not, they all come out into .class files. So some people don't even know they're nesting when they accidentally nest, because you can accidentally nest. You just put one class declaration inside of the other, and you've nested. But then it's hidden in terms of the code, because it's like nested inside of another class. So you only do it when you want to group things together. So let's see, Windows application. We looked at the swing library inheriting from JFrame. Rather than, well, we didn't look at applets at all. And if you're curious, instead of just implementing an application, you can also just inherit from applet or JApplet. And what you can do actually is create a regular old frame that shows up in a web browser. And I'm sure you guys have all seen applets before, but applets, I don't really like applets because they're too big. You load your browser goes to a website and it downloads this applet file, and then it stores the applet on the user's computer in a cache directory, and it runs it from the computer. Really antiquated. Nobody's doing that anymore. Instead, they're just using JavaScript, or they're just putting the code on a server side instead of a client side. So. Let's see, so I'm going to skip the applet stuff. This lecture is kind of getting into the applet stuff. When we looked at the swing library, and when we looked at GUI programming, and we also looked at the action listener as well, and event handling, we also looked at exception handling. I have event handling and exception handling basic minor concept questions that are part of the exam, but they're not, in fact, you can hardly tell, and they're not very specific. So the class must interface action listener, but that's not on the exam either, but anyway. Must define a method action performed. The class implements the action listener. It has an is-a-action listener relationship, obviously, because it contains it. It's inside of it. The method add action listener takes an object of type action listener, so we can add a listener to a component. So we added listeners to components that we're putting, widgets or items that we're putting on the GUI. So a button, it doesn't have to be a button though, we can add it to a text box, label, I don't know, we can add it to the frame. You touch the frame, you touch the window, click on the window and it does something. Actually, all those irritating programs, it follows the mouse around or something like that, or just action listeners. So here's an example. We use the time class and execute an application in its own window, and you can put an event handler to set the time, so the time keeps changing. And here's an example of how that actually would be implemented. So you can cut and paste and use the code if you want to implement the time. So I'm not going to go through the source code examples because these are easy enough for you to download, actually, to kind of run through on yourself if you want to. So we don't have to worry about interclass definitions as well. This basically, the note is basically telling you that for every class, even the internal inner classes, if you're leaving, make sure you sign the roster before you leave. They're leaving. Come and end up being a .class file. So we have .class files that are created from everything, whether it's inside or outside. Don't really need to know that for the vinyl either, but it's just kind of a trivia piece that I don't know if I mentioned. Let's see. I don't really need to know about that. So let's go. Well, I ended actually earlier than expected. So I didn't go over the examples. Is what I didn't do. So that was the by request lecture for those people who wanted the super duper review. Believe it or not, it's about 62 slides, but I went through it at the speed of light because this is all stuff we covered in the course. It's a nice recap. It is labeled number 13. It's everything everyone requested by, well, actually a little bit more, because I just basically took a lecture I thought that covered most of the stuff. But long story short, I would use the final exam review summary I gave you to do as a checkpoint. Do I know about inheritance? Do I know about interfaces? Do I know about abstraction? And then if you can answer, if you know something about the concept, it's multiple choice. So you're going to get the concept. So the only type of programming is knowing the keyword abstract, knowing the keyword extends, knowing the keyword implements, knowing the concept of being able to extend multiple extend one class but implement multiple interfaces. The concept of making the data members private, the member functions public, and the concept of everything that's defined in the superclass being available in the subclass. The superclass, subclass, which can also be a superclass to another subclass kind of concept. The act of actually casting or referencing objects from the different hierarchical levels, treating them as objects. The ability to use polymorphism to make all of the objects equal. The ability to use polymorphism to have a class react differently to different calls from different objects of different types. As an example, a print method that can print a square or a rectangle or something like that, depending upon what it accepts. Actually, the system out is polymorphic because you can system out everything, and you can system in everything if you think about it. So there's a lot of polymorphism built in to the language itself. You don't really need to know, like, the stuff that I did not go over that's in this particular lecture. You don't really need to know, but it's just kind of filling in some different terminology for the same terms that I've been giving you throughout the course. Questions? No? Comments? Concerns? Everybody knows everything about abstraction and polymorphism and inheritance. Didn't cover encapsulation in this lecture. Didn't cover it for a good reason. There's nothing to do with encapsulation. I mean, encapsulation is a concept that just comes in by default. It's like once you make a person, you've encapsulated the concept of the person inside of that object. So encapsulation works with the identity of the object as well, though. So if you have a person and the person flies, doesn't walk, has wings instead of arms, then your identity of that object and your encapsulation is kind of weird. It's like, if you take that person and make them into a teacher, they may not necessarily have all the skills necessary to write, but can fly. So encapsulation is more along the lines of keep making rules in terms of object identities, making a person, a car, a car. Because when you encapsulate and you have a print module, you should be able to replace one print module with another print module because they're both printing. And if we have a person, then we should be able to use a person whenever we need to actually use a person. So we can make a student from a person, or a teacher from a person, or employee from a person, and have that capability. So encapsulation, they also sometimes refer to that as information hiding as well, because you're hiding the concept. You're just implementing it. So you don't have to worry about how age is calculated. If you don't know anything about people. Every year you get a little bit older. But you don't have to worry about that, actually, because the concept's encapsulated into get older method or grow method or something. Or you don't have to worry about how to calculate the area of a triangle, because all you have to do is run area. And so you've hidden the information in terms of the implementation, and you've encapsulated it in the concept of that object and that method or message you're going to ask the object of what's your area. And your object's going to come back and say, hey, my area is this. But we don't know, because we've hidden the information and we've hidden the implementation by the encapsulation of that object and that method. We don't know how it was calculated, so we don't do it manually. So that's the encapsulation concept, but it's not like a programming thing. Inheritance is definitely a programming-related concept because we are extending classes from other classes. And abstraction is definitely programming related. Abstraction and object orientation does come in many different forms, just like polymorphism does. Inheritance is inheritance. Encapsulation is encapsulation. There's like no roundabout way of making that into something else. But polymorphism and abstraction have many different angles to them, as you probably have noticed right now. So the object is the abstraction, the main abstraction of the language. We have also the concept of abstract objects, in terms of abstract classes. We also, believe it or not, the interface is a form of abstraction as well, because interfaces give us the abstract template that we have to implement that's going to give us the concept of what that object's going to compose of, what methods it's going to contain, what data it's going to hold on to, and stuff like that. We have abstraction in terms of what it is we're doing. I mean, we're modeling the real world in a program, essentially. I don't know, I think I've covered all the abstraction examples. Polymorphism, I think I've given you a couple of them already. The object itself can warp from different forms. The object can respond to different messages in different ways depending upon its selection of methods that are available. So if you relate polymorphism with generic kind of behavior, you're probably going to remember it a little easier, only because the object can react generically, can take on generic objects. Abstraction, I don't know what you can relate abstraction to, personally. I don't know. Concepts, maybe? It's conceptual. Abstract is conceptual, from the word. But now you're just going to go around using the word abstract all over. That's really abstract. You know, actually, when someone tells you something that you don't understand, that's not really clear, and they're all over, that's just really abstract. Because it is. It's just like you could be talking about this, you could be talking about that, you could be talking about, you know, I don't know what you're talking about. So that's abstract. And then polymorphic, I don't know, there's no way, I don't know. There's no, well, humans are polymorphic, if you think about it. Yeah, actually, when you're on a soccer field, you turn into a soccer player. When you're on a softball field or a football field, you turn into a football player. You morph. You know, because you're using a different skill set, you're responding differently to your environment. That's actually an example of polymorphism. When you're sitting here in a classroom, you're acting differently than when you're working on a job, I hope. I mean, you're not quite as passive. You're probably doing something differently, I hope, on your job. When I'm here, this is different than when I'm on a golf course. So yeah, people can be polymorphic as well, I guess. An object, you have to think that's what objects, if you think object orientation is mimicking the real world, then you can actually take all of those different concepts and relate them to the real world. Because they are the real world. We have objects that are warping into, you know, shapes that are warping into circles and squares and stuff. It's a circle when it's over here, it's a square when it's over here. It's acting differently, it's warping into different shapes and forms. It's being abstract, it's not clearly defined, and it's just changing dynamically at runtime into what it's supposed to be. And then it's getting inherited. Actually, inheritance is really easy. Everybody has parents, right? At one point, you had parents. At one point, you were inherited objects. So, and then you probably have other inherited objects. So you're a superclass and a subclass all in one. So yeah, object orientation actually does, not to go on a complete tangent, but object orientation actually does mimic the real world if I think about it abstractly. So those are the people who wanted to know what object orientation was about. There we go. That's what it was. Questions? No? Let me stop this video then. So I can have some rudimentary. Actually, I'll say this for people, ITU students here, who are watching a video here. The exam is at 5 o'clock on Monday. 5 o'clock on Monday.